Okay, good morning to everyone. Thank you for your presence. This is a workshop, the first workshop of our project INST, that is Institute of a National Institute of Science and Technology, founded by CNPq from Brazil, and we organized this workshop to discuss some mathematical aspects of artificial intelligence, and we're very happy that many important people from Latin America and also from Europe are with us to discuss some new lines of research on this area. And so I would like to thank the organizers of the workshop, Aline, Morgan, and the scientific committee that gave some ideas, also Roberto Imbuzeiro and Eddie Bird, Lopez, and many people here from NeuroMat that help us to make this possible. Artur, Mateus, Lourdes, Liena, and Stella. I am going to forget someone. So thank you very much to make it possible. So I'm going to introduce our first speaker, that is Joaquín Fontbona from the Universidad de Chile. He's a full professor at the Universidad de Chile. He's engineer from, is right? And his undergraduate course was in engineer, and doctor from the Université Pierre et Marie Curie. And now he's working on some aspect of machine learning and artificial intelligence, and it's a pleasure to have his talk today. So thank you very much, Joaquín.
Okay, thank you very much, Florencia. And I would like first to thank you and the organizers for inviting me here. This is a very nice opportunity to discuss new things from mathematics point of view. This is also my first time at USP, so I'm very glad to be here. Okay, so what I'm going to present is, I would say, it's a mixture of ideas which are already present in the development of what are called generative diffusion models, and also some new ideas, but also which also come from more or less the same realm in mathematics, which is stochastic processes. And actually, this is one of the topics in artificial intelligence where I would say there's more clearly in view what the mathematical objects are. And interestingly, although many of these objects were initially inspired by probabilistic and mathematical ideas, I don't think these ideas probability ideas have been properly used or to understand what to do, how these algorithms work, and how they could be done better. Okay, made better in a way. So this is part of ongoing work with David Felipe, who's a master's student at the University of Chile. And this is more or less the outline of my talk. So I'm going to give a brief overview of what these generative diffusion models are. I will mention a couple of examples. I would say maybe the first, which was become known, popular, and maybe the last and more refined ones. And then what does it consist, the solution of this the problem, okay? What people is actually doing. So I would say there is a gap here between the practice and theory, even if the practice has there is some intuition, there is a mathematical intuition that turns out to be correct, but it's not complete, I would say. I mean, it's one of the things that people discover that work, and then they keep, developing the idea, and they improve it and so on. But exactly what they are doing is not so clear, okay? So in order to give some background on what these methods do, we need actually a little bit of stochastic analysis. So probably not all of you have had a, let's say, stochastic calculus course, but some have. I recognize some. Yeah, so I will try to be, it will be a bit technical, but I will mainly give the main ideas and kind of the main classic results from stochastic analysis that are underlying all these objects and how you can use them, okay? In particular, when applying it to generative diffusions, but there are more general ideas here, I mean, applications, in particular of this, which is called Girsanov theorem, okay? So then I will present kind of an enlarged picture of generative diffusion models in a sense which will include or model simultaneously sampling and training, because so far I would say the focus is on what is sampling in this case, in this setting. But what you are doing, let's say from a statistical point of view, when you're training these models is I mean, okay, you are minimizing some loss function, but okay, and so what can you say something more, have a wider perspective on that. Then I will give some theoretical results and discuss some perspective of this. Okay, so you probably have seen this. So what are these generative diffusion models? So what is the idea? The idea is that you would like to sample from a target distribution that is not tractable, but you have samples of it, available data, and so you would like to generate new samples, okay, artificially. So what you will use is what you want to use is a distribution that we'll call in, which is your input, and typically it could be noise, and some process, some dynamics which could be random, typically, and I mean because of the input which is random, but also because it will have some random component like a random motion here. And the idea is that this process will start, when started from this initial distribution, which is noise, will produce after some time samples of your data, okay? That's the idea. So typically, this initial distribution can be sampled from easily, so really like Gaussian white noise, which is, I mean, very easy and not expensive to sample in a computer, not too expensive. And also, this, I will call this later sampling process, but you would like it to be easily implemented, okay? So it could be an ordinary differential equation or stochastic differential equation for which you have Euler method. So it should be sampled easily once you know what its features are, the coefficients, but you don't know them actually. So the goal is, yeah, how to identify what this process is and implement it, okay? So the basic idea is, so this is the common speech, so one must think a little bit of to understand exactly what this means, but the idea is to use a neural network to learn or approximate, okay, I would say the most likely characteristic of this process, what this process should be, this sampling process, using noise versions of the data you want to sample at the end, okay? So the idea, in a way, is to learn to remove the noise from this, starting from pure noise, okay, and arrive at a pure sample from the data. Okay, yeah, so by simulating this process, you are able to sample something that resembles your data. So let me give a couple of examples. So this was like the first one, which was stated in these terms, which is called denoising diffusion probabilistic models or something like that, from like 6 years ago. So it relies on the following well-known stochastic process, which is the Ornstein-Uhlenbeck process. So you probably know that this process is, well, it's driven by a Brownian motion. It has very nice properties. It converges to a Gaussian equilibrium exponentially fast, independent of the dimension. So the idea is that, okay, we know that this process will go to some random noise, whatever the initial condition, okay? So if I start from data which is representing, let's say, my images of some type, I run this for some time, I will end up with a Gaussian distribution which is pure noise. So what people noticed, and this is something known for already some decades in probability, is that if you run the process backward, the Ornstein-Uhlenbeck process, you also have a diffusion process. And in theory, at least, you know what these coefficients are, okay? So it's again a diffusion process. And so the idea is that if you are able to run this process backward, learn how to run it backward, starting from the, let's say, stationary distribution, which is noise, if you're running backward the process which started from this low data, okay? So this is, yeah, so, yeah, if you start from noise for this backward process, you would like to end with distribution and points distributed like data, okay? The problem, of course, is that this is intractable in the sense that, okay, you have a theoretical expression for this. I will give in a while a description, but you cannot compute it easily, even more if this is high dimensional, okay? So the idea is, the target here is to learn this score function. And once you have it, you can implement this process with a Euler scheme, classic Euler scheme, okay? Okay, so this is the typical sequence of images of a typical cat, except that this is not a typical cat, this is my cat. But well, this is just adding noise. I'm not implementing here any of these algorithms. So, but the idea is that you have this Ornstein-Uhlenbeck process that transforms this cat into noise. So what we would like to do is to have some procedure that, starting from this noise, gives me this type of image. Okay. Yeah, and I will use this notation. The neural network that will learn the score function, I will call it like this S. So theta is the parameter. Okay. Okay, that's, I would say, the first of these models that became popular and was pretty much successful. And this is I would say, like this distilled version of all these methods, which includes various methods, including what are called flow matching, rectified flows, and also this score matching problem, which is called stochastic interpolants. So the idea is the following. I mean, the goal is the same in the sense that I want to produce samples of my data and some noise and an interpolation. Okay, so at the process of introducing noise in order to learn what should be the backward process. But this is, I would say, this is much simpler to implement. The idea is the following: you consider you have a smooth function, so of time and initial position, initial point and final point, which is called interpolant. So it starts from x and ends up at z, and this induces naturally what is called a probability path, a conditional probability path, which is just doing the push forward of the initial distribution of your noise. Okay. So this is called conditional probability path because you know that at the end you will end up in Z, okay? Whatever you started with the distribution you started with. And you can integrate this, and if you integrate this with respect to P data, well, you start with your noise and you end up with the low P data, okay? So this is actually it's a clever idea. And you can implement this easily in the sense that you can easily find an interpolant which makes that your conditional probability path is Gaussian. Just interpolating linearly. Here, beta and alpha are smooth functions, monotone, and you interpolate linearly between your initial noise and the final point. Okay, so this alpha goes from 0 to 1. This goes from 1 to 0, and this conditional path is actually a Gaussian distribution for each time, okay? So this is an important point for all this method, is that conditionally on what the data is, your target, you would like this you would like to be able to generate points, I mean, the cat in different noise stages easily, okay? So the first approach was a rather stochastic approach, where you really introduce noise and random noise at each step, and you look what you get. And here, this is, I mean, there is only one noise source here, which is this. But you will use it at one single time. You don't care. I mean, you really, at some random times, you will have one sample of a noise data point, okay, with some noise that you use once. So it's really equivalent in the sense of final dimensional distributions, okay? And yeah, and once you write it like that with these interpolants, what is nice is that you know what the processes are or should be, in the sense that you can identify, you can write this probability path as the law of this, on one hand, could be an ordinary differential equation. This is the conditional one. And you have a marginal version. And also of some stochastic differential equations. I mean, for the same flow of flows, the probability, the conditional and the marginal, you can represent them as solutions to ODE and yes. There are many possibilities, yes. Actually, it depends on your interpolant. The thing is that this U, which is the good point, the conditional drift, which is called the conditional drift, and also this, which is called the conditional score, are computable from the interpolant, okay? Of course, the marginal ones, you don't know them, okay? But if you want to well, we will see what you do at the end when you really want to estimate the marginal ones, which are intractable, okay? So these are the actual objects. And this, if you are familiar with probability, this looks like a conditional expectation. I mean, well, you can write it a little bit differently, but it is in a way conditional expectation. I will come back to that later. And what else? Yeah, something funny is that, I mean, you have many diffusions possible that could match this flow of probabilities. I mean, as long as you put a sigma here and also put the sigma there, okay? Okay, so this is another method. It's very general, and the idea is the same. So let me just summarize. Yeah, what these methods are aiming to do. So they require and they produce data points equivalent to independent observations of this sampling process, which one to contract at some random points, because you will take uniformly distributed, let's say, points, TI. But this process, this sampling process, you are observing it conditionally on knowing the final values. And that's an important, subtle but important fact. Okay. Well, so what do you do then? And I'm going to explain in the next slide. But so, summarizing, you want to learn a possible sampling process. Well, training, optimizing, well, this the drift and the score to approximate in a way which is not a priori clear, to obtain these marginal functions. Okay, this could be the drift, the score, or the two of them. So I will focus only on the case of the score, but it can be also extended to the case of drift. And what else? And yeah. So what is called, this problem is called score matching. So you have observations from the conditional probability path, I mean, in practice, and you want to estimate the characteristic of the marginal probability path. Okay. Okay. So here is the usual story told here. Okay. So we want to find. We want to approximate this this function that we don't know. So let's consider this loss. So what is this loss? If this is my neural network, which I will train depending on this parameter, I will optimize with some standard, some gradient descent method. And this is just writing for, well, this is an average, but where this time tau is random, uniformly distributed, and it's independent of the data. And the data is distributed, yeah, as I said, you will sample images, say data, and then you will sample, so that would be the x1, and then you will sample at some random time with this, either of these methods, you will sample conditionally on x1, okay? That's what you have. And you will consider, of course, the empirical version of this, which is an average over the several points. Okay, so okay, then people say, okay, this is intractable, so let's optimize this instead. Okay, so instead of course, the function I want to find, I don't know it. So let's use this, replace this loss by this one, where here I have this conditional score. Okay, why not? But why yes also? I mean, x1 is the data. I mean, is the data point. Ah, yeah. Yeah. So, but here this is average over the data points too. Okay, so you sample but the x tau is conditional on the data points. Okay. Okay, and it turns out that it's the good thing to do. So this is kind of I would say it's a theorem, but I rather would say it's folklore. I mean, people did say, okay, we propose this, and we will do this because this was built in such a way that I can implement it. I mean, I have these points, conditional, and it turns out that these two losses differ on a negative constant like this. So, which in particular does not depend on theta. So, if you want to optimize this, you just optimize this, which is people do in practice. Okay. More or less in each paper, but yeah, more in every paper that people is doing something like this, they say, okay, let's do the math. They do the computation, and they arrive at some constant, which they don't make explicit. It's a formula, but they don't know what it is exactly. They always arrive to the same computation. Of course, there is something behind, but it's not very explicit in the literature. So, from the theoretical point of view, we have the following natural question: why this loss? Besides practical, I mean, besides you can implement it and take derivatives and so on. And what is it optimizing? Besides trying just to have similar treatment, what are we doing in practice from a probabilistic point of view? And also, you might have recognized something like this. You start with a square. It's actually in the other direction, but you start with something which is a norm, square norm. Then it's equal to also a square norm, and something else, which is not explicit here, but is, if you put C on the other side. When you look at that, it pretty much looks like this, which is what happens when you compute a regression risk. So you want to optimize this. Well, in the end, you really have to approximate the conditional expectation because this does not depend on your function, okay, on your model. So it is actually something like this, and I will explain in a while. But what are those terms actually? What are the besides being some empirical laws that somebody wrote? What are we doing when we look at those terms? So that is the first question. Thank you. Okay, and there is a remark which is also a quite famous paper in this domain, which states that actually when you look at this, the first loss, the one which is untractable, it turns out to be a relative entropy, and I tell you why, in what sense, in a space of trajectories of stochastic processes. And a relative entropy, you can also interpret it as a maximum likelihood estimator in the space of trajectories, which I will also discuss how you do, but it's probably known for many among you. So if this is an entropy and a maximum likelihood estimator in a suitable way, what is this, which is the actual loss that is being optimized, okay, this conditional one. So that's also part of the motivation, try to understand where all these things live, okay? And if you're a probabilist, even in the first course you have a probability, the teacher will ask you, write the probability space where this is happening, okay? So it's not a, it's useful to understand that all the time, okay? Yeah, and the question is, can we bring some new insights on ideas or even new methods to generative diffusion models by clarifying a little bit these questions? Okay, so let me talk a little bit about stochastic analysis. So this is really classic, but I'm going to tell you how it comes into play and how these ideas are underlying maybe explicitly or maybe not these generative diffusion models. Okay, so there is a classic result in stochastic analysis, stochastic calculus, which is called Girsanov theorem. And it tells you what happens if you have a space of probability space where, well, if you're not used to this, this is a okay. This is some set. Let's say a set of trajectories. This is a sigma field I put in it, which is what are the questions that I can ask and measure. The events of which I compute the probability. Typically, events depending on the trajectories. This is what we call a filtration. So this is really a sequence or an increasing family of sigma algebras, which is more or less telling you how time, what can you access to in terms of information as time goes by. Okay, so these are also events. So there are sub-sigma fields of this. And you would typically put here a probability measure. So that would be what we call a filter probability space. Okay, so assume we have a filter probability space. Let me just recall, if you, in case you are not familiar with the concept, what a martingale is. So I don't know if you can see here, but or maybe there. Or here. Let's take advantage of this giant blackboard. So what is a martingale? It's a stochastic process. Okay, you need some conditions like integrability, but so this is R1. We'll not care too much about it. Well, there is a filtration, as I said, which is given. So what you ask is that this, as a random variable, is measurable with respect to the information you have at time t. And the main characteristic I should say, is the following: is that if you take s larger than t, the conditional expectation of ms knowing ft is mt. Okay. So if you think of conditional expectation, you can think of conditional expectation as a kind of estimator, because this is a projection in L2, so kind of. So this is the conditional expectation is the best approximation of this object using in L2 using things that are measurable with respect to this. So a martingale, what it's telling you is that the best approximation of this value ms random is the value at present. Future value is best approximated by the present value in the sense of mean square error. Okay. In particular, random motion is a famous martingale, and everything that you compute as a stochastic integral with respect to random motion is a martingale, or a local martingale, some extension of the notion. Okay, and there are other fancy objects called semi-martingales, which will appear in a while. I will explain what they are, but semi-martingales and martingales are the ingredients here in this theorem. So what is this theorem, Girsanov theorem, about? So imagine that you have two probability measures here, that you would like to use. Different probability measures can represent different models of nature or beliefs. So you will have that probability measure Q is absolutely continuous with respect to P, if and only if there is a non-negative process, which is a martingale, let's call it D, which has expectation 1 in the reference measure, and such that this D at the final time is the roundly going derivative between P and Q. Okay, so this is something like one of the first applications of Ito formula, Ito calculus that one learns in stochastic calculus. And moreover, by Ito calculus, well, the logarithm of D has this form. So this is the Ito formula. So you need second derivatives, and here you have what is called the quadratic variation. Quadratic variation, it will appear a couple of times. So let me just mention that it's a finite. It's associated to a martingale. So this is finite variation process. In opposition to martingales, which are very irregular in like random motion. Okay, continuous martingales are very irregular. Finite variation, and the idea is that, well, if you consider the square of a martingale, it's no longer a martingale, it's a sub-martingale, which instead of having like constant expectation, it tends to increase because of Jensen inequality, right? But you can subtract something to it to make it a martingale again. And what you need to subtract is this quadratic variation, okay? And this process is unique, okay? And this is, I mean, once you discover this object, you are able to construct the stochastic integral, roughly, okay? For Brownian motion, the quadratic variation is just t, it's time. So it's very easy, but it can be generalized a lot. Okay, so if you use Ito formula, you realize that this can be written like this. So here you have a martingale, and Ito calculus is telling you also that this is this object here. This is a finite variation integral, Stieltjes integral. Well, this is also the quadratic variation of L. Okay, so L is this object, and L is a stochastic integral with respect to a martingale, so it's again a martingale. So that's one of the interests of stochastic integrals. And this is the classic theorem. The question is the following. I have a martingale, some other martingale, let's call it M, in this filter's probability space with, it's a martingale under P, okay? So what happens if I change the probability measure for Q, which is related to P like this? So Gerson's theorem tells you that if you have this martingale under P, adapted to this filtration, this new object M tilde, which is defined like this, I will explain what this means, but is M minus the cross variation of M and L, where this is L. This will be a martingale under Q, okay? So the original martingale is not a martingale, it's something else, and actually it's a semi-martingale, okay? Because M, you can write it like this, and this is a finite variation process. What is this finite variation process? It's like you saw there that M quadratic variation is associated to the square. This is associated to the product. I mean, you can define it by polarization in terms of the object for the squares, okay? It's a bilinear object, and what this makes is that if it's finite variation, and if you subtract it to the product of M and L, you get again a martingale, okay? So it's the extension of that from square to something bilinear. Okay, so the important point is the following. You have a semi-martingale is just a martingale plus something which is finite variation, unadapted. Okay? That's a semi-martingale. The interest of Ito calculus and Ito formula is that once you have a semi-martingale, you apply a F2 function, what you need for Ito formula, and you will remain in the class of semi-martingales. Okay, so that's the point. So in general, in stochastic calculus, it's important to know what the martingales are, this kind of in average preserved quantities, more than that actually. And the semi-martingales is the next good object that you can aim at. Okay, so changing probability measure. I mean, you lose the martingale property, but you are still in the class of semi-martingales, and you have an explicit description of what your new decomposition is, let's say, as a semi-martingale. Yeah, it is, but it's not obvious. I mean, it was not obvious at the beginning. Yeah. And in particular, if you have a Brownian motion, one-dimensional Brownian motion, well, then it is this object B tilde, which will be a Brownian motion in the new probability space. Okay. So what is this BL? Let me give an example, because typically, if the filtration that you have is Brownian, in the sense, for instance, that it's generated by a Brownian motion and an independent random variable, okay, which is typically what you have with a diffusion process or a stochastic differential equation. Well, this filtration has what is called the predictable representation property, which tells you that every martingale here is the stochastic integral with respect to your Brownian motion, in this sense. Well, this is a vectorial Brownian motion, okay? For some nice process measurable in the good way here. In particular, all your martingales are continuous, because that's stochastic integral with respect to Brownian motions are continuous. So if you take this L, you use an L like this in Girsanov, well, your Brownian motion, original Brownian motion, it's transformed like this. You will get, you look at coordinate I, you subtract this quadratic variation. well, this is the object, but this is, I mean, into calculus, this is the object that you have here, is the sum. I forgot to write the sum. But actually, the squares, the quadratic variation between independent random motion is null, and the quadratic variation of a random motion with respect to itself is time. So you get this, okay? So it transforms you a Brownian motion in a Brownian motion with drift, basically, okay? With a drift tip, I mean, it would be called a drift if this depends on xt, let's say. But this is what is going to happen when you apply Kirsanov to a diffusion process. Okay, so let me mention a couple of interesting consequences and useful. You can easily compute or have an expression for the pathways entropy between two diffusion processes. So what is the pathways entropy? It's really, well, the expectation with respect to the reference measure of this function of the density. So it's the same as the entropy, I mean, that you know from any setting. So this is the function x log x. And since q is this, it's written like this, well, you take the logarithm of the density times d, but when you multiply by d and integrate with respect to p, you get an integral with respect to d, actually. And you get the logarithm here of d, which is what in the previous slide was written like this. So this is not a martingale, but if you subtract once this, you get a martingale. So it has zero expectation, so you end up with this, okay? So this is the expectation of the quadratic variation under the new probability. Well, yeah, it will, I mean, this will appear everywhere, really in several, with several interpretations and several roles. So first, if you have two diffusion processes, so this is where I was more or less announcing this, with different different diff coefficients and the same diffusion coefficient, and these are, I mean, reasonable functions, the two distributions are equivalent, okay? I mean, I need them to be reasonable. If I have something which is very singular, maybe I will get singular in the sense of probability behaviors, okay? And it turns out that this, when you do the computation, and this quadratic variation turns out to be this, which is the energy, okay? So you can say, I mean, this is the energy for a process. Which one? For the process, this is under Q, okay? So it is telling me in a way how expensive it is to behave like the process with low P if I am the process with low Q, actually, okay? I must modify the drift in this way. Okay, here is a second consequence of Kirsanov theorem, which is a statistic flavor, which is, imagine that we are observing samples from a given process like this, okay? And I want to estimate in a way which this process is, okay? And I have some models, parameterized models, like could be like NeuroMat, okay? So I want to find what is the best, in some sense, process which has, let's say, the same initial distribution, but it has a drift in my class of models, okay? And I will call P theta this law, and I assume that they have some, the two of them, P and this P theta, have some density with respect to a reference measure that could be just, let's say, Brownian motion without B. Okay, so if you write so this is something general from statistics. If you write the negative empirical log likelihood, this will converge. And it converges to this entropy. This is, I mean, really for random variables in R, this is completely general, plus some constant, which does not depend on the model, okay? And it turns out again that this entropy is giving you now in the measure P here, also this energy, okay? So each time you have this, in some sense, it's an entropy, and it's a maximum likelihood estimator. And then you realize that this is actually also the limit of what you have in generative models, because you are sampling random times independently. So actually, if you look at this empirical cost risk function, you take the limit. I mean, by law of large numbers, they will converge to the integral, well, to the integral normalized. So actually, what you're optimizing in a way, it's kind of it's an entropy, asymptotically, okay? So the takeaway message here is that the random drift regression, which is being done in generative diffusion models, is equivalent to a reverse entropy minimization, because you are optimizing now with respect to this, not with respect to this. And that is equivalent to a maximum likelihood estimation in the path space. Okay, so let's go back and apply this a little bit to generative models. So this is a, so what's the idea? How can you understand at least the first of this, the reversal one? So assume we have a Norstein-Uhlenbeck process, the stationary one. So you start with the limiting law. We know that it is reversible. That means that, well, the time reverse process looks exactly the same with some other random motion. So the law is constant, given by this Gaussian. So, okay, that's the process that is not aiming to, has not the data as a target. Okay, so I didn't start it from data and do it back, run it backward. I started from the equilibrium. So what I would like to do is to force this process in equilibrium to end up the reverse process in the data distribution. Okay, so what does it take me? And you can show the following. If you call P the backward process when started from equilibrium, Q the backward process when started from data, then you can show that the Q is the unique minimizer of the entropy, of this pathway entropy, over all diffusions that have the final low P data. Okay? So in a way it's optimal. And this is what is called Fermat processes. No, it's general. Each time you time reverse a diffusion, it's the optimal that hits the target given by your initial. With respect to a reference one, it doesn't need to be the. I mean, it must be the same generator, but not a stationary version. Okay, and let me just, if you want to know what it actually is in mathematical terms, this score function. It's related to what is called loop transform. The idea is the following. Say that short. Call phi the density between p data and p infinity. So you can assume that it is absolute. I mean, your pictures of cat. A picture of a cat could eventually appear as noise someday. So that's what it means. So by Ito calculus, if you consider a Cauchy problem with this final condition at time t, capital T equal 1, then this process is a martingale. I mean, this function. I mean, you evaluate the function in this case, this was the time reverse stationary process. This is a martingale. It turns out that this is the function, the process L that appears in your density, where you have the logarithm of this solution of the Cauchy problem. And, well, you know under the new law, the transform law, that you will have low P data at the end, because this is how you constructed the density. I mean, it's the density at the final time, but it's also the pathways density. Okay. And by Gersonov theorem, this is the dynamics that you will end up by doing this change of measure. And we know that it's the same as the other one, because this is also a minimizer of the entropy. Okay. So it's the same process, and this must be equal to plus alpha minus plus the score. So you find that the score satisfies this relation. Okay. I mean, you need the solution to this problem. Okay. So all of this is. I don't know if it's written somewhere, but it's. I mean, it's reasonable probabilistic folklore, I would say. Okay. So what is the score matching, if we look at things like this? Actually, yeah, this is what was remarked in this paper. The thing is that this the score matching is actually an entropy. So it's the entropy between this process, which is the law of this process, which is what I'm going to implement with eventually with my neural network, with the good one. But for any neural network theta, I build this process. So it's the entropy between this process and actual time reverse process. So here, I mean, what we can say then is that the maximum likelihood. Yeah. So this is what people remark, that this is a maximum likelihood estimator. But the thing is that this is not the statistical problem that we are solving. The statistical problem that we're actually solving at the end is when I have conditional samples, not the true ones. Okay, so I'm never actually, I mean, at the end, yes, equivalently, but I don't have data for this maximum likeliness. Okay. Okay. So, what does minimizing this mean? Okay, that's a question we will answer now. Okay, so we will enlarge the probabilistic picture and enlarge what we're modeling with these probabilistic objects, not just the diffusion that we will use to sample, but what are the objects that we are using to train. Okay, so yeah, this is what I call, this is a probabilistic model for sampling and training. Okay, so this is the actual observation model. As I said, we are looking at, we're looking for this sampling diffusion process that we don't know. I will write it generally like this because it could have the score and the drift. And we're given data points from this. We assume we are observing data points from this, but it's conditioned on the final value, okay? Which are the photos, the pictures, the data. Okay, so a good question here, in order that I can compute things and understand what's happening, is whether this new process, these conditional trajectories are still diffusion processes. Okay? And that's not a trivial question. It's not a trivial question because I should have something like this. Let's say I have I will aim at, I know what the form is, but we would like to have something like this. Still some random motion. And here I have a drift, which is this conditional type of drift. Okay, so this drift contains information about the future. So this Brownian motion cannot be the same as before, okay? Because, in order to write the diffusion process, I need this Brownian motion to be, you have only randomness at time 0, and then the Brownian motion, which is independent of what happens at time 0. So in a way, what I need is that this information, I learned it at time 0. Okay, and find a Brownian motion which, is independent of these two things. Okay, okay. So, in other words, I would like to work with which I would call Brownian motion with respect to this filtration instead of the original one. Okay, the original one is generated by x0 initial data, this Brownian motion, but I want a Brownian motion in this filtration where I know x1 from the beginning. Okay. Okay. So this last question is the motivation of what was called the theory of enlargement of filtrations, which is really a quite ugly theory. The way it was written, maybe in the 80s and 70s, this is pure good old French school of probability, so they really didn't care about somebody else understanding their papers. So I will give like a reinterpretation of this, which is more or less mentioned in the literature, but it's not really used. But if you use that, you can understand more and do things with it. Before that, I wasn't never able to. I should say that this theory became very popular in mathematicians and in mathematical finance, because it was used to model the fact that you have insider information. Let's say, how does the dynamics of what is the asset price model that you see? If you know that it will, it's random, but you know that the outcome at the end of the month will be this value, okay? So there were lots of questions that people studied about insider trading. Okay. Okay, so let me give a classic example of this. What happens in practice? Just imagine sampling diffusion is just random motion. You want a process which looks like random motion, does not have any drift, and that samples, the law of random motion at time 1, okay? Of course I can use random motion, but I want to write this random motion in a way that is informed of the final value, okay? So I want to write random motion conditionally to its final value as a semi-mapping, as a diffusion process. And the question is already, is it a diffusion process? And the answer is yes. So yeah, I want to use this filtration instead of FT. So, this is a classic result. I think it's dupe. So this, again, is no longer a martingale in this enlarged filtration, but it's a semi-martingale, and it is a diffusion process, and it is this one. So, well, X is my Brownian motion, so you can see who B is at B hat, and you have this drift. And it's interesting expression because here you have X1, which is fixed. So I mean, it's you know it from the beginning, and this drift is kind of not very nice because it explodes at time when t goes to 1. Okay, because it must match this, it must arrive at it. Okay, so but well, this is the good. But there is a good Brownian motion, so you can find out what it is from X, which is independent of X1 and well, initial condition here is 0. So this is a good decomposition, okay? And actually, well, we know that the Brownian motion condition on having a given value X at time 1 is what is known as Brownian bridge, okay? So this is the stochastic differential equation for the Brownian bridge, okay? Okay. So a couple of remarks here which are important for what follows is that if you have your Brownian motion in a given filtration and you enlarge the filtration by something which is independent, I mean, you remain a martingale. Okay, it doesn't do anything this to your Brownian motion or to a martingale. I mean, if in the largest filtration, which includes its independent variable. Okay, so that's a good thing. And the second good thing is that, okay, so if I have any probability measure which is absolutely continuous with respect to the product measure, what I have here, my original process, and here I have this independent variable, by Girsanov, it will again still be a semi-martingale. Under this, I mean, if you're looking at a law which is absolutely continuous with respect to this. So that's what we are going to use in order to write this condition process as a semi-martingale or diffusion process. Okay, so this is some notation. This is the conditional law of the process up to time t, given that at the end I'm at point y. Well, this is the law of the data actually. So I can write this is just what is called the disintegration of the law, of the pathway law, with respect to the final value, okay, this identity. And we will make the following assumption, which is called J, I guess, after a paper of Jean Jagot in the 80s. And it's the following. We will assume that this law for t between 0 and strictly 1, and I will explain why. So this law, I mean, this the law of the joint law of the path and the final value up to time t is absolutely continuous with respect to the product law. Okay, so it's a bit strange, but well, this is a notation for this product law, and well, yeah. Typically, why is this excluded? Because if you want to go up to time t, well, typically x1 will depend on the trajectory of the process, so you cannot expect it to be absolutely continuous. In the case of the Brownian bridge, I'm giving you x1. So the law of the process, so the law on the right cannot be absolutely continuous with respect to a product measure, which is the product measure of the Brownian motion and the Gaussian. But I know I mean, if you forget the conditioning, what you're asking is the bridge target in the point x, y should be absolutely continuous with respect to Brownian motion, to a Gaussian, which is not possible because it's a direct. So it's natural that you don't have t equal 1. And in the case of the Brownian bridge, you have the following, which is more or less equivalent to this condition, is that conditionally on what happens up to time t, you have a density for x1, which is a Gaussian, centered in xt, with some variance. And this is absolutely continuous with respect to the law at time 1. Okay? So you have the property. Okay. Okay, so here are some technical consequences. I think I will go fast on them, but this is combining the condition J and the Girsanov theorem. So the first remark is that working in a large filtration is the same as enlarging the probability space to be a product space, looking at the joint measures there. So the X1 you treat it as some exogenous input, okay? So, but the absolute continuity, you have this martingale for each value, y, conditionally on the final value, you have this martingale, which is a density process. Yeah, you can interpret it in terms of the conditional of the transition densities of the process too. So this is the transition density, and what would be the nicest part I would say is that you have this decomposition of the martingale, and you know exactly what the drift is, which is given by this conditional core. Okay. So what happens at the end is that when you enlarge the filtration, it's kind of changing the probability measure, and the Brownian motion is transformed into, this B is no longer a Brownian motion, but this one is a Brownian motion. So you must add or subtract what is called the information drift. This is called information drift. And actually, this Brownian motion depends on X1. Huh? I didn't write here, but it depends on X1. Okay. It depends in a functional way, but it's, yeah. Okay, but it's independent in statistical terms. Okay, so main results, and I think I will be soon finishing soon. Well, the first result is that, well, for this sampling diffusions, from the moment they are diffusions, it's easy to satisfy this property J, in the case of Brownian motion, Brownian bridge. And the dynamics of the process condition, well, has some drift, which is this conditional drift, and which is related to the original one by this relation. So you have this conditional likelihood that appears. And you know what the new Brownian motion is. Okay. Just thought. So let us call P theta the law of the approximating sampling process, which is what I want to implement with my neural network, okay? Would this be theta? So, and I assume that this law is my original law is dominated by this law, because as in the case of maximum likelihood, okay? My models dominate the law of what I am observing. Let's call this law P hat the conditional law. And well, these are product laws, but one is the one which appears in the condition J. This is a T which is strictly smaller than 1. Okay, so this is the dominating product law for my observation model, the condition diffusion. And this is the same, but I changed the sampling diffusion by the neural network law. Okay. So you have these two absolute continuity relations, and also if you compute this entropy between this and this, since the two of them have this independent component here, it's the same as the entropy that we had before in the maximum likelihood, when we interpreted as a maximum likelihood the score matching problem. And we have the following second result. So remember these two absolute continuous relations. We have the following, I would call additive entropy formula, which is, you have a chain rule for the entropies when you have two absolute continuity relations, but it's not additive in the sense that what you will get, one of the terms in intermediate is the expectation of a conditional entropy. So here you get the sum of entropies. So this is the entropy of what I observe. This is condition. This is the entropy of, well, sorry, with respect to the neural network product, the data. They live they're in the space where they're independent. So what I'm going to be optimizing, this is the more or less the end, is this entropy. Okay, I will give an interpretation of this. So it's written, it decomposes in two terms. So the first one is just what is the relation between my observation model, the condition one, and a model where the sampling process is independent of the data. And this is the entropy between the sampling process and the neural network. Okay. which already appeared. Okay, so if we propose a neural network which has the same type of drift, except that, sorry, there's a typo there, except that, I mean, the only difference is the, well, I don't have the score, and I want to estimate the score. We obtain, I mean, this identity turns to be exactly this when I make t grow to 1, okay? So, and it turns out that this marginal score function is a projection, is the conditional expectation of the conditioned marginal given the point where I am, okay? This was the conditional score matching, and this was the marginal score matching. No, this is equal. Yeah, the intractable is this one. It's this one. No, because it was in the other, it was, this is this minus something positive. So this is the minus, this is the plus something, okay? It's okay? Okay, so some conclusions on perspectives, and this is the last. So actually score matching is a maximum likelihood estimation method, but for the problem of fitting a neural networks to n independent data fitting, yeah. What you want to fit is a neural network and independent data points to this conditioned sampling process, okay? So you can expect that you cannot match them because this knows the future and the other are independent. So maybe it's not the maximum likelihood, but it's the less unlikely. It's a less unlikely network with the independent data that fits these observed conditional samples. Okay. Yeah. So this theory of enlargement of filtration gives I would say, a rigorous modeling framework for the role of information, which I think is important in these reasons I will say in the last comment. You can extend this for the typical, I mean, the interesting, useful problems are conditional sampling, where you, for instance, you want to sample conditional to a prompt or text, or conditional to partial information. So that fits very well in this context because you can do gradual enlargement of filtrations and study the dynamics, the different how the dynamics gradually change when you incorporate different information. Okay, so we're working a little bit on that with David, with my student, and I would say there is some interesting point which I'm very much interested in trying to get deep into, is that what this framework gives you is a way of studying actually two problems, which is not explicit in this setting. Is that well, it's sampling and training, but when you approximate the marginal score, you want to do it because you want to generate data from some distribution. But here in the same problem you have the conditional score, and if you approximated the conditional score, you would be able to do prediction. Okay, I mean it's a different problem, but in order to learn how to generate, you use a functional that should be useful to do prediction. Okay, so yeah, so this goes in the direction of this called alignment. That if you don't want, I mean, your generative model to generate whatever. I mean, sometimes you want it to be exact or to be faithful to your data. Okay, so I think there is some ideas to explore in this direction. How can you train the two things? Maybe for some data you can train. You want exactly prediction of what you're showing, or you want something which has the same law, which is not the same question. Okay, so that's it. Sorry. Thank you very much.
Some questions, remarks? I'm wondering how you apply this to a practical problem. I imagine you are assuming your variables are discrete. Here, because this is a very basic question, but so you are considering matrices as the image you show of the cat, and and how you implement in an algorithm, for example, these things? You need to discretize the time.
I mean, there are two parts. One is the training, and actually that's you have to find some way of sampling conditionally to the image. Okay, so one way is, for instance, this theory of in stochastic interpolants is useful because it allows you to do it in a rather easy way. I mean, it's really, you don't need to, nothing algorithmic, just compute some functions. Okay. So if I wanted to implement this, I would rather use that. So this is kind of the theoretical interpretation, but it's not what I would do in practice. And then for the sampling, if you know what your diffusion process should be, the sampling process, the fact that you learn the drift with a neural network means that this function is implemented. I mean, it's in your computer, and you can evaluate it in any point t and x. So what you do is run an Euler scheme with this using this. You discretize in time, and you start from your noise and use the drift that your neural network is representing. So it's not that. I mean, this is rather theoretical, but it's compatible with the implementation. Mm-hmm.
Other questions? Yeah, we need to use the microphone because.
Sure. Yeah. So maybe back to the stochastic interpolants. Can you connect how the change of measure affects the different stochastic interpolation if you change the interpolator? How do all these things play together?
That's also one of the directions which is it's interesting to look at, because it's not clear. I mean, you have many possible ODEs and also SDEs that could fit match the probability flow. So what is interesting, I would say, is that there should be some like optimal ones. At least for the drift, I think there is. There is an optimal one. You can find in terms of some energy criterion what the optimal one is. The point is that it's not so clear what in the practice what you should use. I mean, there are practical considerations I don't understand very well, but I would say the most interesting thing is that even the diffusion you can tune. You can use different diffusions, and people use that to tune, I don't know, some instability problems. It's really, for numerical purposes, it's good to have this freedom. But there should also be, like, I think, there should be an optimal one in some theoretical sense. Problem is that Irsanov on entropy, if you have two different diffusion processes, even Brown and motion with different diffusion coefficients, they are singular. Okay? I mean, in the continuum they are singular, because you can approximate sigma. I mean, the quadratic variation, you can compute it from the trajectories, approximate it, and will converge to sigma and sigma prime. So probability one, let's say, they are singular. The thing is that in practice, you are not using the continuous trajectories. You are using like this sampling, and in that case, the finite dimensional distributions are equivalent. And there is a limit. I mean, you need to normalize. If you put a grid, they are equivalent. If you take the limit, it will diverge. But if you normalize by over the size of the grid, it converges to something which is called the specific entropy, which is an object which also appears from Nina Gantner, Fermer. It's also an object which has an interpretation that appears in large deviations. So I think you can address that question too, of optimizing even the sigma. Okay, but it's open. I mean, it's a heuristic how do what people do now.
So I'm not coming from the. I mean, I'm not from the field at all, but I also heard about this approach based on optimal transport, when you have some distribution and then you have a flow to play with this. So is this what you have been talking about is related or is different? Could you say something?
Yeah. Interestingly enough, the problem of the Schrödinger bridge, I wanted to talk, but I didn't realize it was too long. is better understood from a theoretical point of view because it's a more complicated object, and people who implemented the diffusion generative models were more aware of the theory. But yeah, what you do then is that you, I mean, the good process, not at the level of just what would be the maximum likelihood or estimation, is that you minimize an entropy, but I mean, you try to find the best, the process that minimizes the entropy given, I mean, you're given the marginals. Okay? You give the marginals and it's a given, and you choose a bridge, the law of a bridge. It's called reciprocal class process. So you want to find the best Markov process that has less entropy compared with respect to your, I mean, the best Markov process in a way that has the same breaches, and not the marginals that you're giving, but it also optimizes the marginals in the sense that I give you two laws, I mean, couple x1 and x0, and when you optimize, you must do some iterative procedure, and actually you are only not only optimizing the drift, but you're optimizing the coupling between the x1 and 0, and the coupling that you obtain when sigma goes to 0 is the Wasserstein distance. Okay. So that you probably have seen that when they show you, okay, I have cats and I have dogs, and I match I give you the dog which is closest to this cat. So this closest thing is because you iterate this in order to also make the coupling, the optimal coupling between the marginals. So it's related.
Okay, let's thank again Joaquin, and if you have more questions, we have a coffee, so you can ask him there in the coffee. Thank you very much, Joaquin. We come back at 10:45. Okay, let's continue with our next speaker. That is Paola Vermolén. It's a pleasure to have her she here to talk in the workshop. Paola is a friend from many years. We share some events in the EVP and the other regional events. And it's a pleasure. I think it's her first time in Sao Paulo. Yes, I think so. Okay, so she's going to talk. Well, she's a profesora of the Instituto de Matemática y Estadística Rafael La Guardia from the Universidad de la República in Uruguay, and she's going to talk about graph representation learning for complex networks. So thank you very much.
Thank you, Florencia, and thank you all the organizers for inviting me. We hope to provide this week to work a little bit also. So what I'm going to talk today is about graph representation learning for complex network. We can traduce it as graphs. But okay, this is the team. We work in this field. Are all from the Universidad de la República, Institute of Mathematics and Institute of Electric Engineering, and Gonzalo Mateos, that is also Uruguayan but works at the University of Rochester. So, okay, this is a little bit about today and this workshop. For us, is our old good friend probability and statistics methods, or machine learning just a few years ago. But it's also true that there are more data, more complex data, and also much more computational power that changes a lot, that changes the game in such a way. So in this week, what we are going to see, I hope to see in the talks that are, okay, we seek for mathematical statistical guarantees, optimality, conversion rate, error control, modeling, as we see in the previous talk, and also to recognize pattern and structure. We want to create general frameworks that help us to understand better what is going on. So in this talk, I'm going to talk about some algorithmic advances and also modeling in graph representation learning, where the input is complex network paragraphs. Maybe for the configurate, we can talk about the reverse question about how can AI contribute to math, but this is a very different question. Okay, this is the agenda, a little bit of machine learning on graphs, and in particular graph representation learning. Then I want to talk about a specific model that is random dot product graphs and its inference method called adjacency spectral embedding. Then we present our algorithmic advances for this problem, how we generalize it to directed graph, that is a particular case, I say, and then we present a new generative weighted model that we can also prove some inference guarantees, statistical guarantees. And then I come back a little bit to the complex networks. So please interrupt me if you want. I think it's more friendly if we can talk in the middle. So machine learning on graphs. Potentially we have three inputs, a graph represented by a matrix, as an sensitive matrix. Sometimes we have features on the node, some signal, let's say, and we can also have edge attributes. This is less frequently, but it can be. And there are also types of problems in a very rough classification. Clustering, for instance, when we have information on the nodes and we want to cluster to detect communities, this is, here there are our papers, this is the network of archive, and we want to cluster the papers given the area. No, you have to put which is the code of the topic that that paper goes on, and you look at the codes that are included in the bibliography of the paper, and this is the way you can cluster the graphs. This is link prediction. Okay, we want to do some, for a new node, where are the links to a knowledge graph, and you want to predict which are the relationships of the edges with other nodes. And we have, in this case, we classify but all the graph classification or regression. We say this graph. In this case, I think that is if this molecule has antibiotic properties or not. So you classify all the graphs. For today's talk, we will assume that there is no signal on the nodes. Oh, okay, there is no signal. We have only the graphs. I have the reference for these two. Okay. Well, graph representation learning. What is it? We want to given a graph with a given adjacency matrix, possibly weighted. We want to learn the dimensional vector representation. For each node, we want to get a vector in D, which D less than n, to have a dimension reduction that preserves somehow local and global properties of the graph. So we go to the graph domain that is discrete, to a continuous domain, a Euclidean domain, where we can measure distance, we can calculate angles, and so on. So the output is what we call a node embedding matrix. We stack all the vector representation for each node, and this is just a draw. For each node, we have a vector in this embedding space, and we want that the geometric relationships in this space corresponds to some relationships in the graph. Okay? And then, okay, in the end-to-end pipeline, then you can apply your favorite machine learning method in RT. Okay? We are not going to talk about this part. We are just focused on getting good representations in this embedding space. So this can be this framework, encoder-decoder, is a general framework that we can say we can express much more of the different types of encoding and that you can imagine. An encoder is this part, as I just mentioned, from the graph to RD, to the low dimensional vector. The decoder is the way we construct these embeddings to reconstruct some information. In particular, in this case, I say about node neighborhood in the graph. Okay, I want a decoder that reconstructs the neighborhood of the node. Okay, this is just to represent the space, the encoder. This is what we call the encoder. I say, the decoder here, we have to define all we want. This similarity measure is what we are trying to reconstruct. It can be all the adjacency metrics. It can be the neighborhood, as I said before. In this case, it's just a pairwise decoder because I'm just looking at the relationship between two nodes. It could be all the adjacency matrices. This is the similarity measures. You can choose the same, then try to reconstruct the number of neighborhood, the structure, another properties. If it's only not pairwise, but it's general, you can try to reconstruct the path between nodes. So this is the similarity that you choose. And then you have to define a distance between these two objects, and then there is a choice there also, the square root, the square norm, Frobenius norm, what you want. There are all of these are decisions, and each decision is probably a new method. So, and then what we call shallow embedding is simply that the encoding is to choose the row of this matrix. It's just this. GNNs, graph neural networks, are deep embeddings, and they take into account not only the node but features on the node, and aggregate this information. Thus, it's a deep embedding. So this is just a picture, also encode in in a vector, and then the code to reconstruct the neighborhood. So this is, as I mentioned before, what we do is to optimize an encoder-decoder to minimize a certain reconstruction loss, this L that you also choose. Okay? So this is what we call graph representation learning. Train the encoder and the decoder so that the parseway node relationship can be effectively reconstructed. This is in I say, loosely stated, because then you have to choose L, you have to choose the similarity, you have to choose any. And here, this is took from the Hamilton's book. A lot of very well-known methods can be written in this context. These are the decoders, square root of the norm, the dot product. This is, okay, not only the adjacency matrix, but power of them. Okay. There are several different choices that gives you different methods.
This similarity may be discrete or continuous, right? You can have
Yes.
Any possibility.
Any possibility.
Also the binary graph.
Yes, yes. Okay. Now I will present this particular model for random graphs. In this case, we are going these graphs. We assume we put the embedding in the model in somehow. We assume that each node of the graph has associated a latent variable, a vector x, and that the probability that there is an edge between two nodes is given by the dot product between these vectors.
So, Vale, in
Sí.
the training of this whole thing, you assume that you have a lot of graphs, and the training is many graphs?
No, it's
like
one, you can do it
and
from one graph.
Okay.
Yes.
And do you do negative training? Do you provide it with certain
Depends on the problem, but yes, you can do negative training. For the previous, in here there is. Okay. Thank you. Okay, so we have a graph, a random dot product graph. Each node is endowed with a vector, and the probability that there is an edge between these two nodes is the dot product of this vector. Okay. So, what if you do given this vector, then you simply flip a coin with probability. For each edge, there is a probability given by this dot product. So we have a natural, if we call X the matrix that has all these vectors stacked as rows, then the probability of matrix connection is given by this product, X transpose. Okay? Each entry of this matrix P is the dot product between files and columns. And so you have for each pair of node I and j. Okay?
And I suppose you do something so that they are only in the positive ordinate, so that these numbers are positive.
Yes, we assume at the beginning that all these vectors are such that the dot product is between 0 and 1. There is our probabilities. Okay? In fact, we will assume in the future prove our theorems about the consistency of the inference method, that these xi, these embedding vectors, are sampled for a distribution that verifies that the image is 0, 1. So these inner products are rotation invariant, and so if we choose another vectors, another matrix that is a rotation of the original one, then we have the same probabilities. So we have our problem is identifiable modular rotations. Okay, if we have all the embeddings and we rotate all the same, we will have the same probability of connections of edge. So this model is a generalization of Erdős-Rényi graphs. We can obtain Erdős-Rényi by simply embedding the deleted position being a square root of the probability P, dimension 1. Stochastic block model also are a particular case of these models, and are special cases when we have more latent position models that use here a function, not only the dot product, but general functions. But you can approximate this with RDBG models. So there are, in a way, generalized classic models. So how, now the first question. We have a graph. We assume that it comes from that is an RDBG model. How can find these embeddings, this latent position? Okay? What is the best choice for these embedding positions? So the main assumption is the adjacency matrix is a noisy realization of P. We have a realization of this matrix P, and so the expectation of the adjacency matrices will be P. And then we can make simply a least square regression for that. Another possibility will be to use a maximum likelihood approach, but we are going to expect that N is large enough, and so it could be computationally inefficient. Okay? So this is the problem. And then if the matrix I is real and symmetric, in this case, the graph is undirected and weighted, so the matrix I are zeros and one, then this have a solution that is the best rank D approximation with positive definitive matrix. So it's the classical spectral decomposition. You have the spectral decomposition of the matrix A, and then approximate it by by taking only the D largest eigenvalues and the corresponding eigenvectors. Okay, we approximate this product. Here we consider only the matrix. This has size n times D. Okay, with the largest eigenvalues and the corresponding eigenvectors. This is the solution. Then the diagonal matrix, we split the square root for each one, and these are x transpose. This will be my estimators. Okay. So, one example, classical. If we talk about graph, it should be the Zachary's Karate Club, and then, well, I don't know if everybody is aware of this graph, but it's a classical two communities, and every method that aims to be a good method should be able to separate these two communities. So in this case, we apply this method, the adjacent spectral embedding, and these are the two communities that are orthogonal. Here, orthogonal embeddings mean that the dot product is 0 or near 0, and then there is no edge. The probability of being an edge is too small. So we can, making an angular clustering, say, you can identify these two communities, and here the largest, the vector, the embeddings with the largest norm represent the more connected node here in the graph. Okay? So this is nice in the sense that they are easy to interpret. Orthogonals are less connected, and magnitude indicates how well connected this node are. Okay? So this is also an embedding for a stochastic block model. This is a synthetic example. There are 3 communities. This is the adjacency matrix we observe. We know that is a stochastic block model, so we can recognize easily the 3 communities. This is our reconstruction, and this is the embeddings in dimension 3. No? So you can recognize easily the 3 communities, and also that the inter-community probability is larger here than here, so you can recognize also these parameters. So what are the limitations or further questions about this inference method? Okay, again, the composition, we have to calculate eigenvalues and eigenvectors. That is a scale for large graph. What happens when we have streaming settings for dynamic graphs? I have not only one graph, but another. I have a sequences of graphs arriving, and we have to recalculate all the eigenvalues in the composition each time. This is a question. So, okay, there is another. There's not really an issue because it worked anyway, but in fact, the original matrix A has 0 in the diagonal because there are no loops, but X transpose has always positive values in the diagonal. So in fact, you want to solve this new problem with a mask that the mask has ones and zeros in the diagonal, only to force that the diagonal is 0. But that is for this mask, but for a general mask, we can use this formulation also to cope with missing data. Not only to put zeros in the diagonal, but put zeros also in places where we don't know, we do not have the information about the presence of assets or links. So what we proposed was to use first-order non-convex optimization method to solve this problem. That is, use stochastic gradient descent to solve this problem. Okay. So what we expect to obtain with this is a better representation, because we are solving the real problem with this 0 in the diagonal, to cope with missing data, and also to have a lower computational cost, especially when we have a sequence of graphs. And we will see that more or less we achieve this. So what are our algorithmic advances with respect to that? We are not the only one that study, of course, matrix decomposition or stochastic gradient descent for optimizing problems related with matrix factorization. But what we do, okay, is the classical gradient descent method. In a step, you choose the direction of the gradient, learning step, and apply it. In this case, we can calculate explicitly the gradient, and we know it can be proved that for this case, the adjacent spectral embedding is the global minimum. It's the unique global minimum. So we have global convergence of the gradient descent. In fact, the stationary points are to use any subset of D eigenvalues and eigenvectors. All of them, any choose of D, not the largest one, but any choose of these will be, the gradient will be 0. But the global minimum is to choose exactly the D largest. So for a general mask, that was for the case when there is no mask. Okay, the original adjacent spectral embedding. When we put a mask, we can prove only local convergence. Okay. Okay, we don't have global commerce because the mask a priori could be anything. I could put all zeros and I have no information. So there is no result. We would like to have a result that say, okay, if the mask verifies such or that, then you have a better result for conversions. But we have local conversions. And we conjecture that we can prove global conversions when we use the mask that makes zeros in the diagonal, but proof coming soon in the next workshop. Okay, and when we use block coordinate descent, that is, you actualize row by row, assuming all the rest is fixed, and you actualize by row, then we have, in a cyclic fashion, then we have better performance also. And this can be done because this is a particular form of the gradient and the mask M that allows us to resolve each one of these problems closely, with an explicit form, not by applying gradient descent. So, some numerical tests. There are some results and some figures. So in this case, we simulate a bipartite graph that simulates two-party Senate, because there is a paper where this kind of data are utilized, so we mimic them. So the nodes are the senators and laws, and there is an edge if that senator votes for that law. The goal or the assumption is that senators of the same party will vote for the same laws, because the party proposed the laws. It's not always the case, but it should be to recognize this relationship, these communities. So in this case, the circles are the parties, and these two are the laws of each party. So the law and the senators of the same party are aligned, and we have here the two communities. All of this, it's okay. But this group here is the law that everybody votes, okay? And then here, these lost crosses are because senators, much of, I shouldn't say much, but maybe they are not present at the votation. So we don't have the information if they vote or not. So the absent, if we put a 0, because I have no information, so I input with a 0, then what we have is that these laws are not aligned with the senators. I say no, these are senators, missing senators. They are not well aligned with the rest of the party. So when we use our gradient descent algorithm with the mask, then we have this good alignment with the previous, okay? So we have a better representation of what was happening. So this is a real example. Is quite similar to the previous one, because it's the vote in the United Nations General Assembly. And again, the problem is to identify the missing data with zeros or using our gradient descent. And here also we choose this example because there's a paper in social science that study this data set. And in this example, I think the year is a particular year of the sequence. And here, where we have United States and Russia, here South Africa and France, and I don't know what the numbers, these numbers are lost. So one thing one good thing of this representation is that effectively Russia and the United States are orthogonals at the moment. South Africa, here it seems to be even far away than the United States from Russia. It's quite awkward. And they both almost identically to USA, but they were present only in 30% of the calls. And France also is less aligned with United States of America, and only they have only 6 votes in difference. So when we when we input here, quite strange. Okay, there are the arrows, and then this is our method here when we input with using the mask, and then we have now France and South Africa well aligned with the United States. That is what really happens. And also, these are the laws, and here I'm not explaining what there are, but also there were more coherent in the clustering of the laws. So, using the gradient descent with the mask for missing data is useful. Okay, what we are doing here is to use it for embedding multiple graphs. When you have two possible situations, you have a given batch of graphs, a given fixed, and you have to embed all at the same time. If you embed one by one, then you have to compute all the decomposition each time, but also for compare it could be difficult because of the rotation invariant, because I don't know if they are aligned or not if I calculate it independently. Okay? And then also it is possible that the graphs you don't have a batch, but you have a sequence. The graphs are arriving one by one. Okay? There are some proposals for that case. For example, when you have a batch, they put or they stack or horizontally or vertically the matrices and compute a giant spectral embedding for that. But in this case, we propose to use, if we have a batch or a sequence, to use gradient descent and then use that solution as warm start for the next one. Okay, that's the conditional, the initial conditional for the next one.
But the new embedding nodes, you initialize them at random.
For the first ones, for the first one, you initialize at random, then you have a solution, and this solution is the initial condition for the next one. Yes. Yes? Or no? No. In this case, we assume that that all have the same nodes. Then we will vary the numbers now. We can do also this, and for this you use the initial condition, the previous one, and a row that you initialize, solving first another problem to avoid rotations of the embeddings. Okay. So, that's what is say here. Again, first a synthetic example. Here are two communities. In one example, what we do is we have a stochastic block model with two communities, and at a certain point, one node changes community. Okay? Change belongs to one community, then belongs to the another one. So if we do this method, what you have is this embedding and this embedding. So it was a rotation between one moment and the another one, and only with this small change. And for gradient descent, everything remains equal. Here is the change that changed from one on another, and the rest stay at the same place. And also, if you continue to move nodes from one community to another, in this case, our error remains stable. We don't increase the error at a time, and in the other proposals, the error increases. Okay? So, making this online gradient descent are stable, and it seems that it's uniformly bound. Now, when the number of nodes varies, deletions of nodes is easy because I simply erase the row of the matrix corresponding to that node, and what happens when we want a new node arrives. So if we initialize with this method proposed by Levin that is simple and consistent and preserves alignment, then we use the embeddings of the previous one for all the rest of the rows, and for the new row, we use this solution. Then, again, we have the same picture as before. Our error remains small and stable, and for this case, which can be used iteratively for the new nodes coming, but the error increases because it accumulates previous errors. Okay? So, yes?
Do you have an idea of how that would compare to the embedding you have obtained if you have taken this additional data point together with the others in the beginning? How sensitive it is? If you train with n plus 1 points from the beginning, you get an embedding. But now imagine that you train with n points, and you add the n plus 1.
I don't know. We didn't try.
Okay.
We didn't try.
But geometrically,
no, because
can you imagine what is going to happen?
I think that it will be, but it will remain stable because the stochastic gradient descent tends to move to the minimal cost, and change in rotating will be too costly, I imagine. So we tend to do the solution that doesn't not change much. We would like to formalize it, but that's the idea. So, and how it works in time, in computational cost. Okay, our implementations are Python-based in our computer, not optimized at all, and they are. I say that they are comparable. I said so. The cost is really promising when compared with stochastic, with singular variable decompositions implemented in C, implemented in programs very optimized. So, okay, just. For the moment, what we see, what this algorithmic proposal to solve the HSS spectral embedding, that the best, the good thing it has, that it can handle missing data, and it can be applied in dynamical settings. Okay, but up to now, the matrix I was binary and symmetric. So undirected and weighted graph. So what can we say for the case of directed or for weighted graph? I imagine I am talking too slow. No? Okay, so for directed graph, there was also an existing proposal that it was, okay, now I have two nodes, two embeddings, two latent vector associated to each node, one representing the outside, I say, relationships from me to the others, and the other vector representing the others with me. Left and right, arrows pointing out or pointing into me. And then the probability of existence of an edge is the dot product between the left and right vectors for these latent positions. So it's quite the same. Now we have these matrices are not the same, are two different matrices. Before was X transpose, now we have X left, X right transpose, but is the same idea, okay? Now in the spectral decomposition, this matrix A is no longer symmetric, so we have to do the singular value decomposition, but it's almost the same idea. We have the singular value decomposition. Here are the singular values. We split square root for each side, and this are the estimator, the adjacent spectral estimator for the left, and this is for the right. Okay. Here we don't have anymore the same matrix U. We have the matrix U, the matrix V. Okay. So the ambiguity in this case is no longer up to rotation, but to any invertible matrix T. And this was not previously, as far as we know, not reported in the literature. We say, okay, the directed case is almost the same, but for comparing graphs, embedding graphs could be much worse. But we propose to solve it in this way. We are again minimizing the Frobenius norm with a mask, but when we use this restriction, that they have orthogonal columns, then everything aligns. And we have the same ambiguity as before, with always rotation ambiguities. So we solve this. Now we have to solve this problem in this manifold, in this matrix manifold. So we implement the, classical Riemannian gradient descent of this manifold. You compute the gradient and project, and then do a retraction. We have to do all the computations, but we follow the classic step to make an optimization over a manifold. Okay, there are. I think this doesn't matter. This is the 3-step. Computate the tangent space, computate the Riemannian gradient, and then make the retraction. You move you move your gradient for the tangent space, and then you come back to the manifold. Okay, what we do here was to verify the robustness to the initial condition, because okay, we are doing gradient descent. So we simulate these benchmark graphs, Lancinetti, Fortunati, Radici, and we initialize, I don't know, several times, 75 random initials. The graph was 16 communities, so we choose D equals 16. This is the adjacent spectral embedding, the optimum, and then all the realizations in the limiting of the gradient descent. So we think that is, we don't have a theorem there, but the performance seems to be okay, even less than the adjacent spectral embedding. So what we do for weighted, I'm accelerating now a little bit. Okay, what we do for weighted graphs. Okay, very good. Okay, for weighted graphs, how we can extend this RDBG model to weighted graphs. So our proposal is to include, now the adjacency matrix will be a general matrix, W, that represent the weights of the edges. So what we are proposing is that each node now has a sequence of latent positions, not one, not two, as in the directed case, but all sequence, and that the dot product, the idea is to maintain the good properties of that the probabilities are given by dot products. Then the first moment is the dot product between the first coordinate of this sequence. The second moment is the dot product between the second vector of these sequences, and so on and so forth. Okay? So we identify with this sequence all the moments of the weight distribution. And then we say, okay, what we are doing is, this is what is writing here. For that case, before, the dot product should be between 0 and 1. Then now this subset should be an admissible moment sequence for a random variable. It can be whatever we choose. And then we specify the moment generating function of the distribution. Okay, so what we are saying that now, given the latent positions, all the sequences of the latent positions, the moment generating function of the matrix of the weight should be of this form. Okay? We specify all the moments of these random variables. Okay, so in fact what we have now is a sequence of matrices, each one of them of the same form as before. Okay, for each moment I have the same aspect as before of X transpose. Potentially it could be even different dimensions for each moment. Okay, the dimensions of this vector could be different, but for the moment we are assuming that we have all the same dimension for all the sequences. Okay, what are the advantages? Okay, we can recover the vanilla RDBG. We have, in fact, it's non-parametric. We could have different per link different distributions. Before there was another proposals where the dot product were identified with the parameter of a given distribution. Okay, all the weights have the same distribution, and the parameters were dependent on the dot product. We are making a non-parametric proposal. Okay. Also, we can extend to direct graph by including a second sequences of vectors, and the inference of the embeddings we can use the same as before, but for each moment, for each power of the matrix. Okay. Okay. See, that's clear, more or less. Okay. In this case, we assume that we have a stochastic block model, but the weights are normal or Poisson, with the same mean but different variance. Okay? If we only, and then here are the first coordinate of the matrix, the first moment, the estimate for the first moment, the estimate for the second moment, and the third moment. Okay? Then, if we look only at the first coordinate, is the mean. So we can distinguish these two different weights, these two communities. For the second moment, there are more separate, but when we see clearly at the third moment, the distributions the communities are well identified between the Gaussians and the Poisson. Okay? So if you have, for example, methods that use that assumes the same distribution and only see at the mean, then these cases are not identified. Okay, well, here are the cross are the real values. In stochastic block model, remember that we have all the information, the theoretical information. We can compute explicitly the embeddings. And these dot lines represent the variance that we can calculate explicitly. So this is our results for consistency. We are assuming two important assumptions. We assume that this matrix, for each k, the second moment matrix has full rank D. That is, for this D full rank is necessary to have a eigengap between the first D eigenvalues and the rest, because if not, we don't have the correct dimension identified. And then we will assume that the weights are subwaveable. For this type of distribution for the weights, we can prove asymptotic consistency and central limit theorem. There were previous results, but there uses bounded weights. With this family of subwaveables, we can apply it to unbounded weight. Okay. And here, okay, our first result was not in this norm. This norm to infinity means that we have convergence uniform for all the k's, not individually for each k, but uniformly for all k's. So the embeddings of all the nodes are asymptotically consistency, and the same for the asymptotic for the central limit theorem, where we can identify. I didn't write here because it's quite long, but the covariance matrix we can calculate also. Everything here is up to a rotation, because, as I said before, these are invariant to rotations. So some examples. Okay, this is what we will expect. There are simply the first 6 moments for a stochastic block model. Also, everything follows the theoretical results, but also has the problem of estimating moments, because to estimate moments of higher order, you need more and more data. Okay, so here we compare. These are 2,000 nodes, and these are 200 nodes. So, and this is the first moment, and this is the fourth moment. So, for the same moment, for the first moment, it's okay, but it degrades the fitting when the number of nodes is not too high. With 200 nodes, the first moment is okay, but the fourth moment is not okay. So this is a classical statistical problem that should be taken into account here. So also we want that our model was a generative model. So we want to generate graph that follows this model. How we generate these models. So you have this admissible moment sequence. Okay, this IJK, and then we want to generate a matrix. We want to generate weights in such a way that the moment of these random variables are equal to the provided ones. So you have this x, we have the x, we estimate the distribution, and then we sample it to construct the graphs. So this problem, in fact, is not related with graphs. You have the moments, and you want to generate a distribution that verifies these moments. So we use these results and we maximum the entropy. So the solution is with the maximum entropy. We solve this problem. We solve the problem of maximum entropy. In fact, we propose a dual problem that is easier and more stable to solve, and it can accommodate for discrete distributions. We started with the simple case, okay, this finite discrete distributions with finite number of states, and if you have the same number of moments than the values that it takes the distribution, then you can solve it explicitly. It's in terms of the Vandermonde matrix, but everybody knows that is very bad conditional to solve numerical problems, but you can solve it more stable with Chebyshev polynomials. That was a suggestion of Mauricio. And then for continuous or mixed probabilities, you solve the maximum entropy problem. In fact, when you have a discrete distribution with less moment than the values it take, you use also maximum entropy. And then here again, the first case, a simulated scenario. We simulate a stochastic block model with this discrete weight. Then you have the theoretical embeddings. With the theoretical embeddings, you calculate the moments. With the moment, you solve your estimation and sample for a collection of graphs. And then we study some statistics on the graph. So we recover the degree, the between centrality, the minimum geodesic distance. So the graph we generate follows the same local and global structure of the graph. Okay, and then for a real network, okay, in the simulated case, it works well. And then for a real network, we use as input the spectral embedding. So there are inexact estimate of the moment. When the moments are exact, we recover well. When we have a noisy estimation of the moment, we do the same. Here, this is the year of the championship, football championship. So we use this data. These are national teams of football, and the links are the number of matches they play between them. The color is the confederations, European, South America, and so forth. And then we generate, okay, that's what I say, we have approximate moments. We generate graphs and, okay, see what happens with the same statistics. And then, okay, we have a fitting that is not so good as in the synthetic case, but it follows the properties of the graphs. Here are the communities. In much of the case, in almost 80%, it recover exactly the 5 communities, and somehow we have one community of more. And this was the indices to see how good there were these communities compared to the real ones. So there is, okay, I say that not too bad fitting to the original communities. So we can use these things to have a test bed of real networks. So, okay, it's very large. Okay. Okay, what we have to do with real networks, this is a model, RDBG is a model, and a model that can capture all the complexities of real network. We have an approximation where we can do calculations and prove things. So some things that we want or to express about the limitations of these models will generate dense graphs, not the observed sparsity patterns of very large real networks, but that can be done by including a density factor that scales, that scale accordingly to have consistence, but to blur some edges. So that I think that it can be done. Okay. This matrix P is positive semi-definite by definition. So some heterophilous, what a node connects has more probability to connect to different nodes, not to similar nodes. That will be negative eigenvalues, and then how can we done in this case? How can we do in this case? There are some proposals that are generalized RDP that is to include a matrices of 1 and -1 between the dot product, or a generalized dot product. But you have to learn what are the number of positive and negative values. Okay, what is the correct dimension D? All the theorems work if the true dimension is used. Okay, now we have a work in progress with Florencia and Saye to find the correct dimension. But at the same time, there are some theorems that say that in the space of graphons, using the cut distance, any graph can be approximated by a stochastic block model for sufficiently large D. So there is something that the problem is this large D. So I need an infinite dimension. This is not very useful. And then we say, okay, how can we do the same with fewer dimensions? And then we are thinking a little bit about hyperbolic geometry to include in these models. But it's still very, very work in progress. So thank you. And I have an invitation. This is a school in Uruguay in November about LLMs, so models, language models, so you are invited.
This November?
Mm-hmm.
Okay, thank you very much, Paola. Questions? Do you have some questions? I only have a very basic question, but have you tried another similarity measures instead of the dot product or no? Because no. But in principle, the gradient descent algorithm works for many other.
No, but the dot product gives you this form. No. Here is this form, XX transpose.
Yeah.
This is the form of.
But you can use another interaction that gives a convex function or not.
Yes.
To use
Yes.
gradient descent.
Yes. A priori, you can. Yes.
Other question? Okay.
Thank you. Yeah. So for the moments you do simultaneously the embedding of, let's say, k fixed moments. As
One graph.
yes.
The moments are of the random variable. No, continue. No.
Okay. Yeah. Yeah. No. So my question was going to be about. For the purpose of the, let's say, detecting communities or some other learning task in the network, do you know how many moments? I mean, you have an idea of how many moments would be useful in what setting to deal with? What is it related to?
Well, it depends. Because imagine you have a distribution, a weight distribution per link. You have a distribution. Imagine it's the same distribution, are all normals, and maybe the community are correspond to different means of this distribution. Communities here is about links, and community normally is about nodes. So that depends a little bit if you want to recognize different properties of the edge distribution or about the nodes. Maybe in that case you have to use some signal for the nodes that includes the information about the weight or something like that. The notion of community is not a little bit is. Yes, it's fast. The idea, community is, we are similar between communities and we are dissimilar to the other communities. And then you can simility or dissimility as you want.
Yeah, so in the first model, in the very initial one, in which it was like factoring it as x transpose times x, but with a mask, what kind of theoretical results are there? How many? So, for instance, if I, under which conditions does this first order algorithm converge to the global optimum? What is known in this sense?
Okay, I think that there are not much results about that. What we proved was for general masks, local conversions. You have to be near to the optimum. And for the case of the mask that has ones and zero in the diagonal, then I think, well, we prove using Garcia-Trillo's results, Lu and Garcia-Trillo's, we proved that the landscape was benign in a sense that the possibilities are were classified. You have good directions and directions, but we cannot prove from their global conversions. So we are trying to modify. I think that finally we should move from this framework, so this result from Garcia-Trillo's, and use another result. But for this particular mask, we think we can prove global conversions because we already we see it with empirically it works with any random initialization. But for a general mask, it's clear that we cannot prove it. We have to find conditions on the mask that makes that the first order method works, but we have advances in that. We have not advanced in that.
So, so my question maybe is related to Joaquin's question. So in many cases, we don't observe the edges. Perhaps you observe just something, the signals in the nodes of your graph. And suppose that, I mean, the edges of the graph was generated by the RDPG model, but they are not observed. And do you think that something could be done? I mean, similar to what you have presented to us to deal with this situation? Like you still want to, I don't know, to embed your, maybe the vertex, the nodes, or they are not. I mean, I can give an example which is closer to what people here in São Paulo have been doing in neuroscience. Usually, the neurons, they are. I mean, there is a natural graph associated to it, but then these graphs are not observed in general. What you do observe in yeah, or maybe if you, the embedding that they naturally have. I mean. They observe the spikes, for example, the activities. Yeah, but it could be more general, you know. And do you think that such approach could be done? I mean,
Yes, there are methods to make graph inference with the covariance matrix or something like that, no? But maybe you can construct, okay, if you assume that the model is an RDPG model, if you can say better than this type of thing, I don't know. It's a good question. Maybe if the signals of the node gives you information about the edge of you see, yes, and then you can, yes, you have like you have an estimate weight distribution, and then you can simulate graph with this distribution, and then see if it fixes it, recovers some of the information previously. Yes, I think that like this, just an idea can be tried. Yes.
Okay, more questions? Okay, let's thank Paul again. Thank you very much for this nice talk. Okay, so now we have a break for lunch, and then we come back at 2.
So, welcome everyone for the last talk of the day. And now we have Marcelo Finger, which is also our colleague here from on the Institute, on the Department of Computer Science. And he will speak a little bit about the neural network into some kind of functions.
Hello. First, thank you all for having me here, listening to speak. I work with neural networks in the real world. I have projects with the neural network that started during the pandemic to try to identify health problem in your respiratory tract. I have networks with for the cement industry, which is a multi-centi-billion industry that's out there. People probably don't know anything about it. And I have also been working with the language, especially Portuguese language, and also Brazilian indigenous languages. But here I'm not going to talk about anything of that. Like, I have been working since 40 years ago with AI, and as a student I was a logician. I still am, okay? And talk about bridging the gap between logic and neural networks. Also, I'm from the computer science department, so if you don't know anything about what I'm doing because you think, oh, these people, computer science, what do they know about mathematics? Stop me, okay? Have no problem explaining your ignorance of this air. I can filter that. I've been doing that all my life. The basic idea is how to predict or how to verify the workings of a neural network. We can do that with programs. We pay a very high price. It's very computational, expensive, and I can explain to you what that means in a while. But we want to do that with neural networks. We want to do, for instance, want to know if a neural network can reach a certain outcome. So instead of giving the input and asking what's the output, I'm giving the output and asking, is it reachable? Okay, but how do we prove that it's reachable? If you have a neural network, you can try reach certain values and you fail. And all you can say is, I failed. That doesn't mean that the neural network cannot achieve that value. Here, I'm trying to show you a way to prove how to do that. Okay? So we can invert a neural network in a sense. And other things like robustness. We can provide a perturbation, or we can define what kind of perturbation keeps the same classification of a neural network. How we do that? We will compile an entire network a logic formula. It won't be a classical logic formula because classical logic has only two truth values, 0 and 1. Okay, totally insufficient. So I'm using this non-classical fuzzy logic called, I'll pronounce it correctly once, okay, Łukasiewicz logic. But I say Lukasiewicz, I cannot say Łukasiewicz, my Polish is not that good. And in that logic, why do I choose this logic? Because it has the one set of right properties for that. I don't have shares of this logic. I don't earn anything by using it, okay? But it has some interesting properties, and I'll try to describe to you what those properties. Actually, the logic itself doesn't have the whole set of properties, and our work was how to go around that, how to fix it. And this is our contribution. This is joint work with Sandro Preto. He's now a professor at the Federal University of ABC. He was previously the postdoc student here. And together with him, we developed the result. First, I'd like just to mention briefly, this is an homage of Tony Hunter. Tony Hunter was a professor at the UCL London Department of Computer Science who just died a few weeks ago in a mountain accident. He got lost, called his wife, "Oh, I'm fine, I'm just going back to the path," and then he was found dead a few hours later by helicopter at midnight. He was a very good friend of mine. We did a PhD together. It was my pleasure to bug him a lot. He was that, prototypical British man who very polite, and I tried very hardly to move him out of this position, but I couldn't. Well, he was like that. I mean, nothing I could do was able to move him out of that. But so this is just one small brief detour. Okay. So the overview of my talk. Sorry. And since most of you are not very familiar with the mathematics I'm going to describe, do interrupt me if I become very incomprehensive. Whoa. So this overview is how to represent a network into a formula in that kind of logic. It's the Lukashevich logic with infinitely many valued, countably many, okay? And how to do formal verification with that. So summary, okay, I take a neural network, I transform it as a Lukashevich infinitely valued formula, and I use that to representation to prove properties about the neural network. That's all, okay? You can go out, you understood everything here, fine. So what are the main ideas? A neural network is a continuous function, okay? And continuous functions can be densely approximated by piecewise linear function. What's that? Okay, I'll do a one-dimensional so this is my input variable, this is my output variable, some continuous function in an interval, anything. And then we can try to approximate it with a piecewise linear function, like that. Okay, you can do better than that. You can do, and then take this. And we can keep on densely, between every approximation and the real function, we can find another one and another one. And this is sort of a Weierstrass theorem, like you can represent any continuous function on an interval with an infinite sum of polynomials. You can do that also with a piecewise linear function. And this generalizes to any dimensions. Now you can think of x as a vector and y a vector. It's also true there. Okay, so this is the idea. You have a continuous function. We're going to approximate it with a piecewise linear function. And so our problem becomes how to represent a piecewise linear function with logic. Okay, that's what we want to do. So continuous functions can be approximated by piecewise linear functions, and we know from the literature that Lukashevich infinitely valued formulas, they represent and they are and can represent all piecewise linear functions with a limitation. And this limitation is as follows. They can represent piecewise linear functions where the linear functions only have integer, with only integer coefficients. And what we want, well, we want approximations, we want to represent with rational coefficients. May seem a small detail, but it's a huge one. Okay, and so this talk is going to be about how to do that, how to move from integer piecewise functions, linear functions with integer coefficients to rational coefficients. Okay, so we want to provide an efficient representation, compute that representation, have an algorithm that you give me a piecewise linear function and I'll give you the formula that represents it, and then apply some magical trick here to verify some logical manipulation to verify the properties automatically. So this logic is quite well known from the literature. There are many well-known provers. Other people developed other provers. So you want to use this machinery already to think about piecewise linear function. So this is the main idea. Okay. So when I had this idea back in 2015 or 16, I thought, well, I have this crazy idea. How come no one had that idea before me? Okay, and the answer was, of course, people had thought about this before me. Okay, so the initial paper was from Amato and Porto. They were the first ones say, oh, we can represent piecewise linear networks as piecewise linear functions, and they provided a way. And the next year, Estevá, Luis Godo, and Montaña, they provided a logic for doing that. But sorry, now computer science speaking, my students here, this logic is too complex. Okay? At that time we didn't know. Now we know this logic has sums and products. It can represent all the roots of polynomials, for instance. And in complexity, in formal computational complexity terms, this means that this logic is p-space complete. Do you know what p-space complete is? No? Okay. Interval for basic complexity theory. What computer science describe as efficient for totally standardizing reasons. There is no reason to say that, but we say polynomial. Can you see polynomial time? Okay. This is the class of all problems that can be solved in polynomial time. There is an exponent that it's always smaller than that, blah, blah. Okay. Here is the X time complexity class in which, well, every X time complexity class includes the polynomial time algorithms as well, but many more. So this is kind of slow. The problem is there is a huge gap between the two of them about which we know next to nothing. So we started giving names to things we don't know where they are. Okay, well, we know where they are. So first thing we know, well, here is the NP class, which contains this one. And here is the co-NP class, which contains the two of them. If you take the intersection, let's call it delta 1. And here there is the sigma 1p and the pi 1p. You take here, it will be the delta 2, then is the sigma 2p pi 2p p4, and this is called the polynomial hierarchy. There is an infinite chain going towards. The union of all this hierarchy is p-space. And what do we know about it? Next to nothing. We don't know if anything is equal to anything else. If there are inclusions in this sense, they are all included, but we don't know if the inclusions are proper or not. But, and this is a big but, if you ever try to implement one of these problems, this is, can sit and cry. This is very hard to implement. This is easy most of the time. So yeah, most of the time it's easy. We have empirical problems, many conjectures why, what's happening, blah, blah, blah. So if I have to implement something here, I prefer to do it here rather than there. Okay? Why? Well, because I've tried. I know that. Not only me, many other people. So this is easier. But this is all, they can be exponential. There can be, say, a level 7 that this is all separated and then it collapses and becomes exponential. We don't know. Since 1971, people are searching for clues and we have got anywhere. Okay? We are incompetent. But, and I still think that complexity theory is one of the main contributions of computer science to the history of human thinking, because we have a way of describing the complexity of the problem. It's not hard to me, it's absolutely hard. Okay, so the human is out. It's not something that's complex to me, I am incompetent. No, it's something that's hard in itself. The problem are hard. The problem is the way this is defined. There is an uncountable number of possible complexity classes. And we keep giving names to them. Not very good ones, I suppose. But, okay, so this is complexity theory. So going back, here, this logic, it's equivalent somehow to, you know, linear programs, but where you have products with variables x times y, not only linear operations. So this is p-space complete. This one was basically, well, you take Lukashevich logics and add all the rationals that you want. Fantastic. Today we know this is only NP complete, but there aren't many algorithms and we don't know how to represent functions here. Here there are ways to represent functions. Very nice, and it's only sigma 1p here. So yeah, it's a little bit worse than NP complete problems. So, but none of these logics have any algorithms, anything, nothing. How to take an input piecewise linear function with dimension n and output m, and generate a formula to do that. So no algorithm, nothing. So we're gonna do that. And we're trying to stay only NP complete. Say only because classical logic is there. So it's the very simple and ors, blah, blah, blah. Yes, propositional classical logic is already NP complete, as was shown in 1971. Okay, so I'll give you a history of the Lukashevich infinitely valued logic. It started as a 3-valued logic. True, false, and tomorrow I'll see. That's the half there was created by Lukashevich in 1920 to deal with Aristotle's future contingents, like tomorrow it will rain. I don't know if it's true or false today, but I will one day know about it. So today this is half. Okay? Then it was, well, if you do for 3, we generalize it to n, no problem. And then mathematicians know what happens if n goes to infinity. So Lukashevich and Tarski in 1930, they defined a logic with countably infinitely many truth values, and these infinite many truth values are the rationals. Okay? So this is the logic. And this is just a curiosity. Just the Lukashevich with n or infinitely many value logics, they are subclassical logics in the sense that all the valid formulas in these logics are also valid formulas in classical logic, propositional logic. Yeah, valid, one valid, I should say. Okay? Okay? Okay, easy. I'm just giving a general panorama of a lot of mathematics most of you don't study. I don't know why. Okay, so what happens? I'll now define the logic. So we start with a set of propositional variables. We have strong disjunction and negation. Negation is very easy. You take the value of the formula, make 1 minus, so a valuation of the negation is 1 minus the valuation of the formulas. This is classical, by the way. If you add 1 or 0, it becomes classical logic. And the piecewise comes from here. If you have this strong disjunction, phi plus psi. So this is the sum of phi plus psi, but it saturates at 1. Okay, that's basically it. We're done. That's all the logic. So satisfiability, we say a formula is satisfiable, or it's 1 satisfiable if there is a valuation that takes it to 1. And for you start up the valuations with the proposition variables between 0 and 1. So here, evaluation is a function between formulas. We start with atomic formulas or propositional formulas. We give them a value in this interval between 0 and 1, including the extremes. Okay. Yeah. Yeah, you can have 1/3, 1/4, anything. Any rational. I don't like real numbers. It's a personal problem with me, because real numbers, they are mostly non-computable. So it's a computational science prejudice. Do you know the name of the paper by Turing, the one that he invented the Turing machines? The name of the paper, On the Existence of Non-Computational Numbers, or non-computable numbers, and an application to the blah, blah, blah. It's a word in German which means the decision problem. Okay? I'll leave the German for you. Thank you. So he proved that there was, and actually most reals are non-computable. So you cannot even write them on the board with infinite. There is no program that generates them. So they are, well, a nightmare. I prefer to stay with rationals. Fine. So this is one valuation, and then for entailment, every valuation that satisfies all the sets, all the formulas in this set of formula, big phi, also satisfy small phi. So here's a big set. I want to take all the valuations that 1 satisfy all of them. They must also 1 satisfy phi. This is the entailment that we're using here. This is not the only entailment. It's not the best entailment. It's the one we use in this work. Okay? Fine. So we are now in non-classical logic. The intuitions go away very quickly. You have to walk with care. Fine. We can define new connectives based on the old ones. So if you apply the Morgan here for conjunction, so this is the strong conjunction, and the semantics is this one. So we add the 2 variables and subtract 1. If it becomes 0, we are stuck at 0. Otherwise, that's the value of the formula. Implication is just phi implies psi is not phi or psi, just like in classical logic. And we have these operators for maximum of the 2 can be defined, and the minimum of the 2 can be defined. Implication by implication, totally standard. We can have even subtraction that stops at 0. Some important properties. If we have phi implies psi, has truth value 1, then the valuation of phi is smaller than the valuation, smaller than or equal than the valuation of psi, and if they are equivalent, the valuations must be equal. So it behaves quite well. What classical property is not valid here? This one. Phi plus phi is not equivalent to phi. This is not a valid formula. Okay, because you can see 1/3 plus 1/3 is not 1/3. All the rest is almost classical. Let's go on. Is it fine? Too complex? I'm gonna state one theorem that's very complex, but I'm not gonna prove it. So now we can talk about functional representation in Lukasiewicz logic. A McNaughton function is a continuous piecewise linear function from the cube from 0, 1 to n to 0, 1, which have only linear pieces that have integer coefficient. So the traditional representation will have variables x1, xn. we say that the value of this function, so phi is a function, is associated to an n variable function such that this is the value of function for every possible valuation. So we can associate a formula with a function. And McNaughton's theorem, that's why I called McNaughton function, from 1951 says every McNaughton function may be represented by a formula. So every piecewise linear function with integer coefficients can be represented by a formula, and conversely, every formula represents some McNaughton function. The second part is easy. You can prove by induction. Okay. The hard part is the initial statement, which was shown by McNaughton in 51 in a non-constructive way. It was a very elaborate argument. Yeah, like this one. Yeah. When you're on intervals, you have, that's a good question, and you take the n-dimensional cube and you split it into polyhedra. So you take every polyhedra to a piecewise n-dimensional hyperplane. That's what happens. And continuously. Okay? So can you imagine breaking an n-dimensional hypercube in many? Good. Yeah, that's exactly what I think. Yeah. No, nothing. You can have no. They can have rational pairs. Yes, must be rational. So this is the McNaughton function. I'll give you an example. So this formula is x plus x, also known as 2x. So we from 2x from 0 to half, and then it saturates. So the red one is the saturation of the 2. And then here is 2, not x. We start with 1, and then it falls. Just look at all coefficients. And this one, the minimum of phi 1 and phi 2, which is just this triangle here. Okay? Just for you to have an idea how to represent a continuous, piecewise continuous function with formulas. Okay? So I've shown you 3 formulas and 3 graphs for it, just for you to grasp the idea. Now we go to rational McNaughton functions, which generalize McNaughton functions, allowing rational coefficients in their linear pieces. And for that, the main idea that we proved is that, well, we can do that instead of one formula, we provide a pair of formulas. So every rational Macnaughton function may be presented modulo satisfiability. Why modulo satisfiability? It only accepts the valuations for phi that make psi 1. Okay? So for every valuation such that it satisfies one satisfies every formula in big psi. Okay? And we didn't say anything. It can be infinite, can be finite, but in practice it's always finite. So, well, how does this work? Does it really solve the problem? We proved that yes, but I'll give you a few examples for you to play around. So, for instance, we can define a constant that has truth value 1/5, for instance. Why? Well, first, we couldn't do that in normal Lukasiewicz logic. There are no constants with value 1/5, because if we had one, it would have a rational coefficient. So the formula phi has value 1/5. It cannot be. It violates Macnaughton. But if we say that the big phi contains only this formula here, so the constant 1/5, if and only if not 4 times the constant of fifth. And if it generates a very complex linear equality, say C15 if and only if 1 minus 4 C15, and when you solve that, you realize that C15 can only have valuation 1/5. It's simple. It's very simple, actually. So this is kind of what showed me, oh, if we make some formulas equal to 1, we can start defining things we couldn't before, blah, blah, blah. So the function, the constant function f of x equals 1/5, the small phi if c, the constant 1/5, plus this formula here. The set of formulas has only one formula, and it goes on. And if you want to represent 3/5, it's like that. There are now computer scientists, they would jump in my neck like that. Oh, so you have an exponential size, because this is unary representation. But you can go around and add as many constants as we want, and you can have binary, and this will shrink back. It won't be exponential. I don't know if you know what they're talking about. I'm reacting to the virtual computer science that's not here. Okay, so we can represent, in this way, we can represent with a polynomial amount of variables any rational. And we can represent rational functions. For instance, f of x is x over 3, can be represented like that formula plus this formula that says basically 3y equals x. So y is x over 3. But x can be anything. It can saturate. So we must say that y has to be smaller than 1/3. And then we can use y to represent exactly this. Just a few examples of how to represent piecewise linear functions here with rational coefficients. Okay, just to convince you that it's possible that way. It seems very simple, but why didn't they do that before us? Okay. Now we're gonna show how to compile a neural network into a formula. We're gonna start with a very simple neural network. It's several layers with activation function ReLU. So it's rectified linear units. It's this function here. It's 0 from -infinity to 0, and then x. So it's and the final node is has it's a truncated identity. It's a ReLU, but it saturates at 1. So here is just choing pong, and here is choing pong point. Okay, understood? Good. So this kind of neural network. We are going to provide a translation to a formula. So yes. Yes, 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 yes. We do have that. But we assume that we had already before we started. So we want to use all that machinery that exists. No, no. I'll show how to reconstitute. I'm going to translate the problems into satisfiability and entailment in Lukashevich infinitely valued logics. Okay? So, but first I need a formula. So functions compute the network are put in regional format. Sandro defined what that means, regional format. It's you have to think about those polyhedra for the full theorem. But in practice, we have this and that, and say we have this, can take the convex intervals, the polyhedra here, and they are associated to functions, and then say here I took the minimum and built that way. And that's exactly what we do in this theorem. Say even if there is one in the middle here, it will appear sometime. There are many details here that I'm trying to escape. It's quite complex. I mean, it's not trivial, but we can put this in. This is the regional format, and so when the function is in the regional formula, then we can compute in polynomial time on the size of the regional format, which is not polynomial, it can be exponential. Okay, but once we have a formula in the regional format, we can have a Lukashevich pair that's polynomial time on the regional format, on the number of regions. But this is a problem that we have been living with. We have already eliminated that. We can go directly from the neural network to here without going through the regional format. Is this working, or I'm just holding it like I'm stupid? Ah, okay. So I'm not stupid. Good. So we can do that. We have an algorithm that computes the formula. Good. Now let's start to encode things here. I want to compute the reachability property. Namely, I want to invert the neural network. I want to know if so suppose f is a function computed by some output neuron of a ReLU TID, which is the ReLU with that saturates at 1, a neural network. And we compute the pair of formulas equivalent to that network. Let pi be a rational, and say let phi1 be the formula that defines this constant rational 1 over b. So I want to see if the formula reaches a value bigger than pi. Does there exist an x that is bigger than pi? And then in this case, we take this phi, take the conjunction of all formulas, plus this definition here, equal plus a times C1b, which this is pi. And I want to see if phi has the value pi. And when this formula is satisfiable, then we know that there exists an input value x such that f of x reaches pi. Okay? So this is one way. So now I can apply, so since I have computed this and that, and this is easy and this is easy too, we can decide if the neural network reaches pi by trying to satisfy this Lukashevich infinitely valued formula. So this is the reachability logical encoding. So in this way we can invert. Just one thing, our satisfiability theorem prover is only NP complete. So this is just like classical logic. It's a little bit worse than classical logic, but it's only NP complete. According, this result only says I need to obtain a pair. Okay. When I wrote this, the only way that I had to obtain a pair was through regional format. Today, this is false. I can pass directly from the neural network to the formula without putting the regional format. Okay? Yes. No, that's not what we do. That's we the way this is solved is by an integer linear program. You can think of that, or you can think as several linear integer programs with an exponential number of columns, but you keep adding them one at a time by a process called column generation. There are these two ways of solving it, so we're not guessing entries to see like that. It's much smarter than what you said. Okay? So there is a gain here for using logic that you didn't have in the first place. And well, we know many properties of this logic. We're carrying mathematical properties to here. Good. Now, is this the robustness classification for binary? Suppose you have a classifier. Says, well, yes, if the output is bigger than, this should be y anyway, but it's terrible. These people in neural networks, X is the input, Y is the output. They cannot change it ever. I've just committed a sin here. This is sigma of Y, the output is yes if Y is bigger than half and no otherwise. Okay, but don't tell them I did that. Okay, it's a sin. And now we saying the following. So I want to do a perturbation of this size, alpha over beta. And I already knew that the values, the output values are A over B. It's supposed to be bigger than half, or smaller than half, if the answer is no. And I want to know, well, if I do a perturbation, does it stay bigger than half, or does it stay smaller than half as it was before? And so this is the mathematical formulation. So I want, at the end of the day, it was bigger than pi or smaller than pi, and now I wanted to do a perturbation of epsilon. Should be delta here actually. So the epsilon and the deltas, and I want to know if the classification stays the same. And this is translated to a huge formula. Blah, 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 entails. This means phi prime is bigger than half. Okay, this is there is a theorem that shows that if if this entailment holds in Lukashevich infinitely valued formulas, then that property of robustness is true, if and only if. So in this way, we can study theoretical perturbations and study reachability problems using the logical representation. We are proving properties on a neural network. Not only trying values, we are actually making strong statements. Not for every neural network, but for these ones. But the fact is, for every neural network that's continuous, there is this Weierstrass, the previous drawing that was here, the Weierstrass theorem that say, well, can be approximated to a degree that you want, so with an error previously established. So we can always find a piecewise linear function and do the following. You won't be studying the original neural network, but one approximation of it. So in the future, what we want? We want to do that for we want to avoid the exponential blow up. We've already done that. Check. Okay, you can start from the network and avoid the exponential blow up. We can try other approximations. We want to start dealing with real world because these neural networks are very simple. And in practice, we use much more complicated things than that. But well, you have to start somewhere. You start with the simple cases, and we go. Then we want to generalize to other neural networks. So at the moment, we are looking at recurrent neural networks, RNNs like LSTM, blah, blah, blah. They're already very complex in the number of layers, etc. And we have to unravel them as they do for training. So you can imagine lots of layers, and you multiply that by 16. That's what's done in practice, and you get a very, very large formula. So because you get a very, very large formula, and we are already in something that's in practice exponential, we're working for approximations of Lukashevich infinitely valued logics theorem provers for verification. We already have good ones, but good ones means small problems so far. You cannot deal with hundreds of layers. Not yet. So we have to go forward. So here approximation means either solving the P versus NP problem, which we're not even near, but we can try. As I said, something you don't know. In practice, and this is maybe a surprise for you, but there is a conjecture that says that every NP complete problem has a phase transition. So you try to linearize the problems by the size, whatever. And here the percentage of satisfiable problems. Think of classical logic formulas. If you have small formulas with very little constraints, basically anything you can guess is satisfiable. So this is 100%. If you think of huge formulas, lots of, then anything will be inconsistent. And then it goes down. Okay? This is what I call first order phase transition. You can think of a SAT problem being, no, not yet. Here is the liquid, and here is the gas. You can think of a problem as being in the liquid phase or in the gas phase. The problem is, if I start measuring the time it takes to solve that problem, when I start, time is what physics call energy. Forget. so little energy I can solve my problem. Here, the very complex formulas, when you try to do a proof, you basically close all the branches, all the possible branches, but it's a little bit higher. The problem is, this is the second order phase transition, and you can think of it as the derivative of the first one. And this turns out in practice. And we say that there is a easy, hard, easy pattern. Most problems are easy, but there is a hard area in NP-complete problems. It's a conjecture since 1991 that every NP-complete problem has that behavior. In practice, once you find a way of linearizing the problems, we measure that. We haven't been able to say, oh, this problem has no phase transition. But many of those problems are easy. They are easy. We see that in practice. Whereas for p-space complete, we don't see anything like that. So, well, it's bad, but it's not horrible. And moving from p-space to NP, we can enjoy this behavior. And sometimes in practice we can solve, sometimes we don't. If you approximate, maybe we'll be able to solve more problems fast. In approximation, there is a value, a measurement that I called patience. So as long as you have patience, you can reach a 0-1 conclusion, or you can give up because you have run out of patience. So if we do approximations, you can have less patience and still have good results. Okay, and that's it. So if you want to hear about me, I have a column in the radio. I talk about AI every other Friday morning. And if you suffer from insomnia, you can download the podcast and sleep tight with my voice. Okay? Thank you very much. These are some of the papers we've written on that we based this presentation. Thank you. I didn't know he was here, but João, your paper is here. Why did I bring you here? Sorry?
Okay, no, the only x-axis is complexity in some things.
Yeah, well, finding a way to linearize this thing. In classical propositional logic, we have to put them in conjunctive normal form as clauses. So we have x1 or x2 or x3, blah, 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 or not x3, okay. And you have a certain number. You can always transform a problem in polynomial size in this format for any formula in classical logic. So n variables and m clauses. In classical logic, this is m over n. So you linearize it that way. For each point here, you generate 100 formulas for the same value of m and n. Actually, you fix n, generate m and n, generate 100. Take the average. The average will give you the percentage of satisfiable, and you take the average time to solve them, and you build this curve. Empirically, one of the failed attempts to prove that P was different from NP was based on trying to reconstruct this curve, and there was two mistakes, one logical and one in statistical mechanics in that proof. I never understood the statistical mechanics problem, but the logical problem was, yes, it doesn't work. Okay, but people have been trying to solve this problem in many different ways. Okay? So this is what computer science worry about. Efficiency. How do you linearize? Because here is problems. And by the way, this is not the only way to linearize the problems. Here, there are other ways have been shown, even in classical logic, to linearize the problems. But there is a conjunction. There is always one way of doing that that provides you with this phase transition, second order phase transition in red. Because that's the real problem. So here have liquid, here have gas, and here you have boiling water, ebullition. And sap behaves just like a fluid. It's an empirical fact. Okay, if you want. Anyway, there are many things we don't know. Okay. Yes, please. Thank you.
I have a more general question. What stops you from using any T-norm fuzzy logic or Pavelka logic, rational Pavelka logic? So why is it Lukashevich? What is it about that you really need for this?
What I need for that is the McNaughton theorem. McNaughton is only valid. Where is McNaughton? Blah, 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 blah. Here. McNaughton tells you that you can represent any piecewise linear function with integer coefficients, like this one. In, say, Gödel logic or whatever, many others, T-norm, whatever you want, you don't have this property. So I'm not interested in Lukashevich, I'm interested in this property. If you have another formula or another logic in which you can represent piecewise linear functions, I can use that. I just don't know about it. There are, well, infinitely many logics that you can define. This one had the property I wanted. That's why I used it. Okay. Yeah, yeah. Like in this logic, here in this logic, L pi half. I always get. Probably it's my mother. No, it's just spam. In this logic, you can represent all the piecewise polynomials. All piecewise polynomials, which is much more than you want. Okay, that's by you're paying. Like if I use that logic, always 3 times. It's always like that. If you use that logic, you would be paying much more than what you need. You're paying p space when you can solve with NP. Okay? Yeah? And here you are in this other leg. We earned 1 step here. And we can implement and have all this for us. Okay? That's what's good of it. And people, I just presented it in last couple of weeks in Portugal. They liked it, and now we are in Wikipedia. If you look on Lukashevich logic in Wikipedia, there is one line. People have used this logic to represent neural networks, and then they cite our 2022 paper. Okay.
And we finished for today, so see you tomorrow.